Video is about three-dimensional vectors or vectors in space, but first we'll talk about one more airplane problem. So an airplane that has an airspeed of 500 kilometers an hour with a bearing of 45 or N45 east. The wind velocity is 60 kilometers per hour in the direction of north 30 degrees west. So if it's north 45 degrees east, that's actually 45 degrees from due north and 30 degrees west of north, so north 30 degrees west would be a 30-degree angle from due north, so that actually represents a 120-degree angle. And this 45 is actually just because a 45-degree angle to the east of north is equivalent to a 45-degree angle from the x-axis. So it just works out that way. So we add the vectors, and we end up getting 250 root 2 minus 30, 250 root 2 plus 30 root 3. Then we do all of these computations, and we end up with 518.777 miles an hour and north 38.586 degrees east, which, if you look at how this might play out, seems to make some sense. So now let's talk about three-dimensional vectors. Extend the distance formula to create a formula for distance that can be used in 3 dimensions. So if we just look at, for example, a box, I know that's a pretty terrible drawing, but if I want to find the distance across 3 dimensions in a box, what I can do is I can find the distance on the floor. So if I call this A and this B and this C, what I can do is I can find the length of this, which is the square root of a squared plus b squared. And then I can do the Pythagorean theorem again in order to get this green length. So that would be the square root of a squared plus b squared square root squared plus c squared. So notice that it's just this squared plus this squared and then take the square root. Well, if I square the square root, I end up with the square root of a squared plus b squared plus c squared. So notice that a 3-dimensional distance, all that is just the squares of each of the 3 distances that we're traveling. So this would be, let's call this the x's, the y's, and the z's. All I would do, if I want a 3-dimensional distance formula, is I would take the distance that I'm traveling in x and square it, the distance I'm traveling in y and square it, and the distance I'm traveling in z and square it, and put that all under a square root. So notice it's just the distance formula with all 3 letters in it. So now let's find the distance between P1 and P2. So if I'm given these points, notice that the x's I'm traveling 3, so 3 squared. The y's I'm traveling 4. And the z's I'm traveling 5. So it's 3 squared plus 4 squared plus 5 squared. I just did these subtractions in my head. So it's 9 plus 16 plus 25. So this is the square root of 50, which you can leave as square root of 50 or simplify to 5 square root of 2. Find the position vectors between these points. So u is from P1 to P2. So that's 0 minus 3, 5 minus 1, negative 1, minus 4. And v is going to be likewise negative 3, negative 4, 5. Find the magnitude of v. So the magnitude of v is just going to be, well, we already calculated the magnitude of v. We did that when we calculated the distance between P1 and P2. So that's the square root of 50. Then we want to find a unit vector in the direction of u. So I'm going to take u, which is 3, 4, negative 5, and divide each of the parts by the square root of 50. You can simplify these, but it's not necessary. So what would the dot product look like in 3 dimensions? It's just x1 times x2 plus y1 times y2 plus z1 times z2. And equivalently, we can still use the magnitude of one vector times the magnitude of the other vector times cosine theta. That would also give us the dot product, where theta represents the angle between the two vectors. So v and w. And how can you find the angle between the two vectors? Well, we can just use this formula and then solve just like we did in 2 dimensions for theta. So it's the dot product divided by the magnitudes of the two vectors and then take the inverse cosine of those things. So if we want to find the angle between two vectors like u and v, we would use this formula just like we did in 2 dimensions. We're going to find the magnitude of u, which is 7, the magnitude of v, which is the square root of 30. Then we'll find the dot product of these two vectors. 2 times 2 is 4, negative 3 times 5 is negative 15, and 6 times negative 1 is negative 6. We add those together, we get negative 17. And so we take the arc cosine of the dot product divided by the magnitude of those two things multiplied together. We get 116.321 degrees, and we can look at a visual of that and see that this angle would be something like 116 degrees in 3 dimensions. So now let's do another problem. Find the angle between these two vectors. Notice that this vector u does not have a j component. So if I wrote it in this form, it'd be negative 5, 0, 2. So when I find the magnitude of u and v, I have square root of 29 and square root of 122. The dot product is 1. Then I do the arc cosine of 1 over the square root of 29 times the square root of 122, and that's not quite a right angle, but it's pretty close. And if we pull this up, we can kind of see these two vectors showing up. So if I graphed this one, this is at 5, 0, 2, or negative 5, 0, 2. See that the positives are going back there. I twirled the graph around just so it's easier to see what's going on. Now, to describe a non-zero vector in space, if we have two vectors, we can describe the angle between them like we just did in these two problems. But to describe where it is, we can't just say there's one angle with the positive x-axis. Notice that we have to describe it in terms of where it is with all three axes, because it could be anywhere in, there aren't just quadrants, there's a lot of different places that you can put it in. There's octants when you have 3 dimensions here. So if we want to label where it is, we have to describe 3 different angles. We have to describe an angle with the x-axis, which we call alpha, an angle with the y-axis, which we call beta, and an angle with the z-axis, which we call gamma. So all 3 of those things are labeled. And then if we realize that we have unit vectors for the x, y, and z axes as I, j, and k, 1, 0, 0, 0, 1, 0, and 0, 0, 1, then what we can do is we can just use this cosine formula and dot whatever vector we have with the I, j, and k vectors representing the x, y, and z axes. And then we can get angle formulas for how far away they are from the x-axis, y-axis, and z-axis. So we're going to use these a lot. We'll just focus on alpha first, and then the other ones follow pretty easily from there. But if I do this vector dotted with I, notice that the y and z components just go away. And since I is a unit vector, the magnitude of I is 1. So if I want the angle with the x-axis, I just take the x component of the vector and divide it by the magnitude of the vector, and then take the arc cosine of it. Likewise for y and z. So if I want to find direction angles for a vector, I just find the magnitude of this vector, which is the square root of 24. 16, 4, and 4 gives me 24 on the inside. So then I just take each component and divide it by the magnitude and take the arc cosine for x, y, and z, and then that gives me alpha, beta, and gamma, which are the direction angles in the x direction, the y direction, and the z direction. So they're really not that hard. And if you forget, you can just use the formula that we have and realize that all we're doing is dotting it with the x-axis vector, unit vector, or y-axis unit vector, or z-axis unit vector. So we have one more example of this with the vector 9, -4, -2. If I take the magnitude, I get the square root of 101. And then I can do the x direction, y direction, and z direction angles with those axes. So alpha is 26.423 degrees, beta is around 113 degrees, and gamma is around 101 degrees.